you have a note sheet that looks like this. So the focus of today's lecture is going to be looking at the electron arrangement. That's what our focus is going to look at. And from these, we end up having these four letters, N, L, M, and at the bottom here, spin, S. These are called the quantum numbers. And for atoms, they have four quantum numbers. They have an N value, an L value, an M value, and an S value. These are the four quantum numbers, symbolized as letters, but each of these letters that symbolize a specific description of the places that we put these electrons, each of them have a cosigning number, and that's why they're called quantum numbers. The first value, N, is the energy level of the electron. In essence, to the Bohr model, this is analogous to the Bohr model, in which this is the ring around the nucleus. Okay, you can think of it as a ring, but really it's an energy level. So, if you are in energy level 1, you are the closest to the nucleus. It's like, think of an apartment building. I'm on floor 1. If I get to the energy level of 3, I've gone to the elevator and pushed the 3 button. I've gone up to the 3rd floor. I am now 3 floors above the ground floor. Okay? The ground floor being the nucleus of the atom. So with that, just like this, so the energy level is dictated by the number, and they go up in order. Okay? You can have N values of 1, 2, 3, all the way to 7, because there are 7 horizontal rows in the periodic table. So the number, the period, dictates the energy level, which you can kind of think of it as how many floors above the nucleus are we. The L tells me the shape of the orbital. And I'm using the word orbital because the word orbital, in essence, think of it as this is the electron homes. This is the places where the electrons reside. Where do we find the electrons? They're not just simply spinning around the nucleus like a planet going around the sun. So these electron orbitals are places that house the electrons. What are their shapes? What do they look like? Well, with that, there are 4 basic shapes of the orbitals. Okay? If you have a shape of an S shape is a spherical shape. It looks like a sphere, a ball, like a tennis ball or volleyball or basketball. It looks like a sphere. If it's a P shape, it is a dumbbell. So if you think of lifting weights, it's a dumbbell shape. D stands for a double dumbbell. So the shape of the orbital looks like 2 dumbbells where the thinner middle part is overlapped, almost forming like an X, where you've got the 4 bigger bulbs in the end in different directions. And the F orbital is called the complex shape, which I'll show and go over a picture of that as well. Now, how do we get the L value? The L quantum number is given to us by a mathematical equation, which is the N value minus 1. Okay, so for example, if I am on the 1st floor, if N equals 1, if I'm on the first energy level, to figure out the second quantum number, the L value of it, we simply subtract 1 from it. 1 minus 1 gives me a value of 0. Whenever we have an L equals 0, that quantum number tells me that I'm talking about a spherical orbital. So on the first energy level, the first ring around the nucleus, there only exists one shape of the orbitals. It's a spherical shape because it can only possibly have one quantum number if you have an n equal 1 state. Now, what happens if we have the second energy level, n equals 2? Well, now we can have an L value that's 1. N minus 1 gives me 1, or it can also have an L value of 0. It would be whole numbers down to 0. So when I'm on the 2nd floor, quantum mechanics tells me that I have a possibility of either having an L equal 1 shape or an L equal 0 shape. Well, if L equals 1, that coincides with a dumbbell shape. So on the 2nd floor above the nucleus, or 2nd ring around the nucleus, we can have a spherical shape or a dumbbell shape, but only those 2 shapes exist. As I keep moving up, if n equals 3, Now I can have an L value of 2, 1, or 0. And as you guess right, the L equals 2 tells me now I have a D-shaped possibility. So as I go up into the energy levels, I start gaining more and more of these different shapes. And that's why as we get up to more and more rings, you can have more and more electrons. Hopefully for some of you now, that light bulb is going on as to why when I go from one floor to the next, I start getting more and more electrons being able to be placed on the ring. It doesn't have so much to do about the size. It has to do about what number of orbitals are available due to the energy level. If once you get to floor number 4, we now get to all 3 shapes. We don't get, once we get beyond floor 4, when we get into floors 5, 6, and 7, all right, so when we get to floors 5, 6, and 7, the shapes of the orbitals just keep on being the same, okay? So we don't get to another shape of an orbital. 4 is all that we find in quantum mechanics. And as you already can guess, if I have an L equal 3 shape, that coincides with a complex orbital. Okay, what else do we find out is, so the shape of the orbital is dictated by letter L, the second quantum number, okay? So the third quantum number is M, and it's called the angular momentum quantum number. What this tells me is the number of each shape we have. So how many of these shapes exist on each of the floors? Okay, if you have a spherical shape, there's only one per floor, which means a spherical shape, when you move it in three-dimensional space, it always looks the same. So I'm going to now, so when we have p orbitals, there are 3 of them per floor. D, there's 5 per floor, and F, there are 7 per floor. Okay. Lastly, when we have an orbital, the last quantum number is S. When I have, for example, a spherical orbital and I have an electron in there, what we find out is that 2 electrons fill each orbital. Each orbital takes up to 2 electrons. And what we find is when we have 2 electrons in that same very tight space, negative charges repel each other. They don't like being next to each other. So a way to minimize that repulsion is by having their magnetic fields align in opposite orientations. So what that requires is these electrons are actually spinning around an axis. One of the electrons spins in a clockwise shape, the other one spins in a counterclockwise shape. So they have 2 different spin states. But what this really truly means overall is that the electrons that it takes 2 electrons to fill an orbital. The only difference between them is that they spin in opposite directions. Because when one spins one way, its positive magnetic field and its negative magnetic field is aligned maybe this way. The other one is going to be aligned negative and positive. And so their magnetic fields are somewhat attracted to each other, and therefore 2 electrons can fill the same tight position. So I know this is a lot of heavy theoretical stuff, but what's the key takeaway from today? So these electrons don't exist in rings. They exist in orbitals that have these different shapes. But in summary, this is the key thing to take away from today. When we are in the first energy level, so when you're thinking of the Bohr model of the atom, when we're in that first ring around the nucleus, closest to the nucleus, what we find out is this, is that we have only one possible shape. Electrons can only be found in an s orbital. And because there's only one of them on each floor, there's only one orbital on the first floor, which is called the 1s. The 1 stands for what energy level we are on, first floor. The s is what shape of orbital we are talking about, a spherical orbital. And as I said, how many electrons can fill an orbital? Since there's only one orbital on the first floor, 2 electrons can fill it. And this answers now the key question, is that there's only one orbital on that floor to have that little bit of energy, and therefore 2 electrons fill it. In the second floor, we now have 2 shapes, S and P. Well, just like before, there's only one s orbital, but now we number 2s. Just like in hotels, where the first floor, all the room numbers are labeled with a 1, like 100, 101, 102. You go to the second floor, 212, 216. They all start with a 2 for second floor. P's, they always come in 3 per floor because they have the x-axis alignment, the y-axis alignment, and the z-axis alignment. So there are 4 orbitals on the second floor. Each of these orbitals can possess up to 2 electrons. Well, 4 times 2 gives me 8 electrons. Why to that question? And the why is the fact that it comes down to the number of orbitals that there are found to be in each of the rings. Okay? And we just keep moving up. S, P, and D, 3s, 3px, 3py, 3pz, but now we get the d's. And how many are there? Okay, now there are 5 per floor. So if I look at the third floor, we would have 3d, 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 and 3d. And these do have letters just like xy. You might have like 3d xy, 3d yz, but I'm not going to show that. For the most part, you just have to know that there's 5 of them. So if I add that up, I've got 1 3s, 3 3p's, and 3d's. That adds up to 9. So there's 9 orbitals. Takes 2 electrons to fill an orbital. That's 18 electrons. So it takes 18 electrons to fill the third floor completely. Fourth floor, S, P, D, and F. Now we get 1 s orbital, 3 d orbitals, 3 p orbitals, my fault, 3 p orbitals, 5 d's, and 7 f's. How would we label them to be perfect? It would be the 4s, 4px, 4py, 4pz, 4 d's, there'd be 5 of them, and there'd be 4 f's. There'd be 7 4f orbitals. That adds up to a total of 16 electrons times 2. That gives me 32 electrons. After that, floors 5, 6, and 7, they all repeat. Okay, they all repeat floor 4. So on floor 5, there would be 1 5s. There would be 3 5p's. There would be 5 5d's. There would be 7 5f's. It would just keep repeating what floor 4 is. So 32 electrons is the most amount of electrons that can fill a ring. We can't have more than 32 electrons fill a ring. And that's pretty much it with this concept. Now, as triggered, the number of electrons that fill an orbital perfectly coincides with the periodic table and the width of each of the columns, because that's how many electrons it takes to fill each of those basic shapes. So, today there's really no homework. The idea of this lecture is just for you to be able to understand why so many electrons go in all these different places and what these things look like. Tomorrow, when you listen to the next lecture, it's going to go over how we do these configurations. And of all things, that's probably the more important thing, but I wanted to give some background information for those of you that really want the answer as to why. This is that theoretical concept that explains why in the first floor there's only hydrogen and helium. Why does only 2 atoms exist on the first floor of the periodic table? It's because of how many electrons it takes to fill an orbital. Okay? I appreciate you for listening. Hopefully it wasn't too much of a snooze fest, and hopefully by listening it does give you some good background information. It helps answer the question why. All right, today's concept is we're going to focus on the last part of the atom. Currently, we have been primarily looking at the nucleus and the center part of the atom. And again, the nucleus contains the protons and the neutrons. And this is, for the most part, is considered to have all of the mass of the atom is found in the nucleus. And we've been talking about concepts like atomic mass and atomic mass problems. We've also utilized, the last lecture was what happens when we have an unstable nucleus and the atom decays into a different isotope. So our focus so far has been on the nucleus in this unit. The last part of the atom that we have to kind of investigate is the electron cloud. Now, most of you come to this class with this idea that the electrons are spinning around in this cloud around the nucleus. You might even have probably a more distinct picture. Instead of it being a diffuse cloud, a fuzzy cloud that surrounds the nucleus that the electrons can be found in, most students come to my class with this idea of what's called the Bohr model of the atom. And this is what was probably presented to you in middle school. In the Bohr model of the atom, the electrons are found existing on rings. This is often called the planetary system model, where you think of the electrons existing in like orbits and they spin around the nucleus. While it's a fine model to be able just to kind of have arrangement of the electrons, it is not really a correct model. The Bohr model is better than the electron cloud model, and then the Bohr model eventually gives birth to the last model that we currently still believe in, which is called the quantum mechanics model. And that's what this lecture will be on, is actually quantum mechanics. These places that the electrons are found in are not really rings, and the electrons just spin around the nucleus in a ring. And the Bohr model states that the electron can only be found on these rings. So the first ring, the closest ring to the nucleus, is called N1. And that first ring, electrons spin around much like Mercury spins around the sun. Then there's the second ring, labeled N2, third ring N3, and so on and so forth. Believe it or not, these rings do correlate to the periodic table. So if you look at the periodic table in your Chem Helper, and you've got hydrogen up here and helium up over here, you'll notice that if you put numbers off to the side, there are literally 7 rows on the periodic table, horizontal columns. Each horizontal row, this is called a period of the periodic table. So the top row, which only contains 2 elements, is period 1. The second row, from lithium all the way to neon, that's period 2 all the way to the 7th period. So those do correspond to the rings. So an atom that gets down to the 7th row, there is as many as 7 rings that surround the nucleus for these larger atoms. Okay? So it does correlate to the periodic table, and this is why the Bohr model does work very well for most things. But in quantum mechanics, we're going to find out that the electrons don't exist as just point sources that are spinning around the nucleus. They exist in things that are called orbitals. And that's what the focus of this lecture is going to be, is what do these orbitals look like, and where are they found, and how many of them there are found. Okay? One other concept that I'll briefly mention is more than likely your middle school teacher said that, okay, I want you to draw the electron configuration for sodium. The element sodium, the atom sodium, if you have an atom of sodium, it has 11 electrons. How do we know that? We look at the atomic number. Okay? The atomic number of sodium is 11. Below it is the atomic mass, which is 22.99 AMU. Remember, that is looking at the nucleus, the protons and neutrons, the mass of the nucleus. It is not getting us at the electrons. For atoms, remember, the number of protons equals the number of electrons. So an atom of sodium has 11 protons because that's the atomic number. That's also how many electrons you have. So one of the first things you have to do in these problems is to be able to identify how many electrons the atom has, which is equal to the atomic number if it's an atom. Well, what you probably did in middle school is your teacher said, okay, you have 11 electrons. Place them around the rings. So if you have the nucleus of sodium with its 11 protons, so it would have a charge of plus 11 because it has 11 protons in it. Your first ring around the nucleus, I can guarantee you in these worksheets, your teacher said on the first ring, you can only put 2 electrons on that first ring. So you put an electron, 2 electrons on that first ring. Now that ring is full. It can only occupy 2 electrons. Then you have to go to the second ring. Well, we have 11 electrons to account for, correct? We've already accounted for 2 of them. The second ring, your teacher probably said, can take up to 8. So you start putting electrons on this ring. 1, 2, 3, 4, 5, 6, 7, 8. If I add up total, that's 10 electrons. I need 1 more. So now I need to go to the third ring. And I put 1 electron on that final ring. This is probably electron configuration models that you guys did in middle school. And this is more than likely where your teacher took you to. Maybe you've done this, maybe you've not. But in past years, this is what students have usually told me. Well, the question for some of you might have arisen is, the question is why? Why on the first ring does it only take 2 electrons? Why in the second ring does it take 8? Okay, in the third ring it takes also 8. Why? Why is that the case? And some of you might have a misconception. The misconception might be, well, the ring is larger, therefore it can occupy more electrons. There's partly truth to that, but it's not the full answer to it. So today we're going to focus as to the why. Why does the first ring only take 1? Why does the second ring only take 8? And so on and so forth. All right, so in your picture demonstrated and showed, if I'm on floor 1, I'm on this first ring around the nucleus. If I'm on floor 3, I am now on the third floor. I'm getting further and further away from the nucleus. Is the pictures go back I have posed before? Why in middle school did your teacher say only 2 electrons can be fit in the first ring? The answer to that question, why again your teacher said on the second ring it can take up to 8 electrons. We now know the answer. Apply. That is where hopefully the light bulb these orbitals. Here's what these orbitals look like. And again, when we have an S shape stands for spherical, no matter how I move this guy in orbital space, as I twist and turn it, the shape of this orbital never looks any different. And this is why when we're on the first floor, or any floor, be it, a spherical orbital has only one basic shape to it. Because it's round, it doesn't possess any other shapes. The p orbitals, here you can kind of see what they look like in real life. Now, you might say, how does that look like a dumbbell? Well, in real life, you think of a dumbbell like that. You can kind of see here are the lobes of the dumbbell, and in the middle, which is the nucleus, remember the electrons can't be possessed in the nucleus. There's that gap, and that gap is where you'd kind of think of having your handle, the thin handle in between. But here's the lobes. But if we look at three-dimensional space, let's say this is the x-axis, this is the y-axis, and this is the z-axis. You'll notice that these lobes are orientated along the z-axis. We call this the pz orbital because the electrons are found in those purple areas bouncing back and forth. That is the home for that electron. It's the pz. This one would be the px, and this would be the py. So as I spin this, if I think of a dumbbell and I twist it, I can have that orbital spin in all three-dimensional space, and its shape looks differently as I spin it. Unlike a sphere, who always looks the same when I turn an object or a ball, it never changes how it moves. But the p orbitals do. So what this tells me is on every floor, there are 3 p's on each floor. Okay. D's, they get more complex. Now you think of 2 dumbbells. So here's a dumbbell, and here's another dumbbell. So now in the d orbitals, you'll notice that there are 5 different shapes of these orbitals. So they come in groups of 5s. F orbitals, if you look at, if a p orbital has got 2 of those lobes, a d has 4 of those lobes, what do you think an F orbital is going to look like? Believe it or not, it's now 8 lobes. So here's a d orbital, and there's an F orbital. Okay, where now it has a total of 8 lobes. Okay, versus the D having 4 lobes and the P having 2 lobes. So it has 8 lobes, and these are called the complex orbitals. And as you can guess it, if there's one S shape, there's 3 P shapes, there's 5 D shapes. How many F shapes do you think there are? 7. You're correct. Let me get to a regular piece of paper here. If you look at the periodic table, you'll notice that there's this block pulled out of it. Actually, each of these blocks, if you think of like the old game of Tetris, there are really 4 blocks that make up the periodic table. Right here. Each of those blocks coincides with the 4 basic shapes of orbitals. This block right here is called the S block. Any element in groups 1 or 2, these first 2 vertical rows, are said to be in the S block because the outermost electron, the electron on the outermost ring, is being placed in that shape of orbital. This is the D block, this is the P block, and this is the F block. The F block has actually been pulled out of the periodic table. So if I were to really draw the periodic table correctly, this is what the periodic table would look like. This should have been a little higher. So when I go across the periodic table, if I were to count, when I insert the F block, if I were to go all the way across from end to end, if you were to count how many atoms fill from one end to the other, if you count correctly, you get 32 electrons. If you count across where there is no F block, but there is a D block and a P block, if you were to count across that, you get 18. If you were to count across just the S block and the P block, which is like groups, rows 2 and 3, you end up getting 8. And if you look at where you have just hydrogen and helium, to go across that is 2 electrons. 2, 8, 18, 32.